Okay, picking up a little bit after we left last time, we were talking about significant figures for pretty much all of last class. And we talked about counting significant figures. We talked about what we care about when we're doing different types of operations, mathematical operators, addition, subtraction being one set, multiplication, division being the other set. And we care about either decimal places or significant figures. When we're doing those calculations, we pick the smaller number for decimal places or significant figures. Today, we are learning the joys of unit conversions and some tips and tricks maybe for problem solving. We deal with a decent or above average amount of word problems. They're not like pure word problems because we're still going to see numbers, but there's a lot of problem solving involved in chemistry. I really like problem solving. A lot of people don't, and it's confusing. I do my best when we're talking through problems to try to show you kind of what I'm looking at, what I'm seeing, the things that I'm picking out, the important information to help you kind of get a feel for what's important and what's not important. If we are solving a problem, it requires some critical thinking. Video games are great for developing some critical thinking, especially if they have puzzles in them. If it's just first-person shooters, probably a little bit less critical thinking skills. I'm a big fan of video games. I think that it helps with critical thinking depending on what games you play. A lot of our problems are not going to have a simple, straightforward solution. It's not going to be like you memorize, okay, we do this equation, we do this step, we do this step, we do this step. Okay, we have this type of problem, we do this step, we do this step, we do this step. We're not going to have a simple framework like that, but a lot of problems reuse the same conversions. So it's sort of like we're playing a game of Tetris. You've got different blocks. You'll be using kind of the same blocks throughout the whole course. It's just a matter of where do you have room to fit in the block? What's the correct block for the situation that you're going into to clear that line? And we can also learn some problem strategies through pretty much the entire course. A lot of our problems can be thought of as unit conversion problems. Other times we will need specific equations, but a lot of them can be broken down into unit conversion problems, even if there's a specific equation that they require. When we're converting units, it's algebra. Units get multiplied, divided, and canceled like any other algebraic quantities, like x, y, and z. So things like centimeters, inches, liters, other units, all behave like x, y, and z. If we multiply centimeters and centimeters, using that middle dot as our multiply sign, centimeters times centimeters, if we had x times x, it would be x squared. In this case, it would be centimeters squared. We can also get rid of units by canceling them out. So let's say that we've got 4.5 grams of lead, maybe, or mercury. I don't know. It doesn't matter. And this has the density with it. I don't remember off the top of my head what the density for lead is. Let's just say it's 11.5 grams per milliliter. What volume of lead do we have? If we set up our problem with the 11.5 grams per milliliter or per cubic centimeter, this way we have grams on the top in our starting number, and we've, instead of multiplying by our density. We've divided by our density, so we have grams on the bottom. That will cancel out with the grams that we have in our starting number. And I crossed them out to show that they disappeared. The units that we have left are milliliters and lead. The number is not really important, but we can cancel out units like this, and oftentimes I'll stack them up in multiple steps. Some things that'll help when we're looking at problems this way, where we're canceling out the units and the units kind of guide our path, that's called dimensional analysis. The grams and the milliliters, any of those units are dimensions, like length is a dimension. If you're in 3 dimensions like we are, right, volume, length by length by length. So something that's helpful, get used to writing every number with its unit. Every number needs its unit. It might have multiple units. Make it a habit. If it has a unit associated with it, write the unit. I know that a lot of you probably don't want to do that. I didn't want to do that when I was learning chemistry. I've gotten used to it. It's not that big of a deal. It's a little bit more writing. Time. If you make a mistake and you've written out all of your units, you've shown all your work, when you come back, it's easier to spot those mistakes. It's also easier to catch them as you're doing the calculation. We're also going to include those units in our calculations. And we need to have diligent bookkeeping on our units. Don't just poof, 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 appear or disappear your units. If you can't show that you canceled it out, then it didn't disappear. You need to be able to show that it disappeared. Otherwise, you very likely didn't do the problem correctly. For a lot of our problems, we are given a quantity. Generally, when I make notes on problems, I use the color green to indicate something that we're given. And we're asked to convert that quantity, whatever it is, maybe it's length, maybe it's grams, maybe it's time. We're asked to convert that to another unit. This would be called the find, and it's fuchsia or pink. So that's kind of like the guide. I'm going to use those colors. I've gotten in the habit of using those colors. So that's going to be the case for the entire class. You're welcome to do that. You're welcome to just disregard that. But just so you know what's going on, that's what it is. So for dimensional analysis, this is kind of what I was showing on this previous slide. We had information that was given to us in the problem, and we used some conversion factor that we were provided with, that we knew off the top of our head, that we went and found in a table, or we asked Google, hey, what's the conversion between these two units? And that gets us to the information that we want. And the way that that happens is the unit that we started with in our conversion factor, we put that on the bottom. The unit that we want goes on top, so that the unit that we want comes through to our final answer. We'll do tons of examples of this throughout the course. We can make conversion factors. The way that conversion factors work in the math world is that a conversion factor is we're multiplying by 1. When you multiply by 1, what happens? You get the same thing that you put in. So we're not changing anything. We're transforming it a little bit. We're changing the way that we represent it. But we've multiplied by 1. It's not actually changing anything other than like maybe the units that we're dealing with, right? That's the goal. So any two things that are equal, we can make a conversion factor out of. Here we've got English units, and we've got our metric or SI units. Question?
I don't know if you said this, but should we be memorizing?
For the most part, you don't have to memorize anything yet, like in terms of unit conversions. You will be provided with an information sheet on exams, and I'll post those ahead of time so that you can see what you're going to get. A lot of the conversion factors I don't expect you to have memorized. It's faster if you have memorized. Usually you'll be given conversion factors. I lean more towards you should know how to do the problems, not you should have everything memorized. You don't have to memorize a periodic table for my class, for example, because that's a waste of time. Okay, if we want to make a conversion factor between ounces and grams, 1 ounce is equal to 28.35 grams. Those two things are equal to each other. So we can set them up this way. Let's say that we want to do this because we're converting from let's say we've got a recipe that calls for 500 grams of some food, half a kilo. And we want to turn that into ounces. We might end up turning it into pounds. So recipe calls for 500 grams of flour maybe, but our scale only measures in ounces, so we need to figure out what it is. Probably go, hey Google, what's 500 grams in ounces? And that works. One way you can check your answers for this, but of course you can't use Google on exams, so it's important that we learn how to do it ourselves. We can construct conversion factors out of this 1 ounce equals 28.35 grams. What we're going to do is divide both sides by either of them. So for the first one, let's do divide both sides by ounces. On the left side, 1 ounce over 1 ounce. It's the exact same thing, so that turns into 1. So this thing that we've got over here on the right is equal to 1. 28.35 grams over 1 ounce equals 1. If we multiply by that, nothing changed because we've multiplied by 1. So that's one of our conversion factors. The way that we have this problem, we're starting with grams. If we multiply by 28.35 grams over 1 ounce, will our grams cancel? No, they won't. We need the other conversion factor, which would be if we divided both sides by 28.35 grams. So let's do that up in this top right corner. So that right side turns into 1, and on the left side we have 1 ounce over 28.35 grams. What do we notice about the conversion up here in this right-hand corner and the conversion on the left side? It's just flipped. You can always flip a conversion factor for free. That would be taking the inverse. The inverse of 1 is also 1. You can flip these for free. The other thing you might notice is that we took two things that were equal. We put one on the bottom, and the other one was on the top. That's how we're always going to construct our conversion factors. So if you can learn that trick, if you can remember that trick, you don't have to show me how you came up with conversion factors. You can just, these two things are equal, and skip straight to the conversion factor. You can skip the divide both sides by the same thing. So this conversion factor that we have up in this top right corner, if we set this out, next to the 500 grams that we have, we've got now grams on the top in our starting number. We've got grams on the bottom in our conversion factor, so those units will cancel out. The ounces will come through, and that's how we would calculate the number of ounces of flour that we need for whatever our baking recipe is. Question?
Couldn't we have just done that like in the first step?
Done what?
Just do 500 divided by 28.35.
Yeah, that's what we're doing. This is just how we set it up, making the conversion factors. Any other questions? Okay, construct some conversion factors between feet and inches and centimeters. I'll give you the equivalents. Not 12 feet, 12 inches equals 1 foot. One inch equals 2.54 centimeters. So make both conversion factors for those. All right, our two conversion factors for feet and inches, 12 inches over 1 foot, and the inverse, if we flip the top and the bottom, 1 foot over 12 inches. So we just took one of the sides and put it on top. We put the other side on the bottom. For inches and centimeters, 1 inch over 2.54 centimeters. And our other form of it is the inverse. Flip the top and the bottom, 2.54 centimeters over 1 inch. When we're converting between units, it's important that the final units are correct. Wrong units is a wrong answer. This will get some of you in a little bit of trouble on the exam because I'll be asking for specific units, and that might mean that you have to do a unit conversion, or you might have to use a specific conversion factor, and if you don't do it, then that's going to be a wrong answer. So make sure that you're checking that your units are correct. If your units are correct, especially if you set up the whole calculation and you can show that you canceled out the units, that's a good sign that you probably did things correctly. It's also important that you consider whether the magnitude of the answer makes sense. If I'm trying to convert 70 inches into meters. 70 inches is 5'10". That's about how tall I am. If I'm trying to convert my height into meters, and I somehow end up with 0.5 meters, I know that a meter is about 3 feet. I shouldn't be getting 0.5 meters. So in my brain, little alarm bells would be going off. Hey, this is not correct. We messed up. Something is wrong. Consider the magnitude step. That's something that you'll build the more that you deal with the units that we're using. You'll hopefully start to build some sort of a sense of what a correct amount is. One analogy for this might be if you ask your friend to pick you up an energy drink from Save Mart or something, and just Venmo you, request the money from you for it, and they say, all right, here's, give me $10 for that energy drink. Hopefully, little alarm bells are going off in your head, like that's way too much for an energy drink. And you can be like, hey, show me the receipt, because that's not right. It should be like $4 at most. And we already talked about this last point. Conversion factors can be inverted, flip top and bottom, because they're equal to 1, and the inverse of 1 is also 1. When we're converting between units, it can be helpful to set up a solution map, a set of steps. That show the route that we take to solve the problem. If you set up a solution map every single time that you do a question, this is not like writing out all the conversion factors, but if you set up a solution map, it breaks it down into the individual steps. And the more that you do that, the more you'll see, okay, well, this is a step that I know how to do. I know what I can convert to from grams, for example. I can convert to moles. I can convert to kilograms. I can convert to ounces. You'll start to build the habit of putting together these solution maps. When we're doing solution maps, we are focused on the units and converting from one to another. If we're just doing one step, a solution map feels kind of silly. But in the future, in later steps of the class, we are going to be stringing together 3 or 4 steps. That means we'll need 3 or 4, sometimes maybe even 5 conversion factors or equations that we're going to link together to get the correct answer. And so a solution map can be helpful to prevent us from doing unnecessary work. We can think about our units and help that plan our route that we're going to take. It's like if I had planned out when I was turning around on Reed to go a different way, I would have walked over to Frankwood instead of driving like all the way over on Goodfellow to Parlier basically and then coming back over. So planning ahead can help save unnecessary work, or in my case, unnecessary driving. When we're solution mapping, it might look something like this. We'd write out, we're going from inches to centimeters. We can do that in one step, and then I would usually write the conversion factor in underneath the arrows. The other direction are green centimeters over here. That's what we're starting with. Centimeters to inches, that's also one step. We've just flipped our conversion factor top and bottom. When we're doing these problem-solving strategies, we're going to identify our starting point, the given information. So sometimes if I'm trying to get some classroom participation, I might ask, what are we given? And then you can start listing off like the numbers that we were given. Maybe we're given a conversion factor or a constant that we need to solve the problem. And then we'll underline those in green. I'll also ask you, what's the endpoint? Or what's our find variable? Our find variable is usually linked to a question word. So who, what, when, where, why, how. Any of the words that we would use to ask a question. Our find variable is usually going to be right next to or very close to that question word. And then we'll set up our solution map from our starting point to our end point with a set of arrows. Usually I put my mid steps in blue. So writing everything out in its colors, given with some arrows going to our find or whatever our last unit is going to be. There might be some intermediate unit. And then we can write conversion factors under our arrows. This is kind of saying the same thing as the previous slide. You want to sort your information out, come up with a solution map, and then you can solve your problem. Usually the way that I will write out my solutions or my calculations is that I will have our given over on the far left. I'll have however many conversion factors we need in these separate boxes. The vertical lines just serve to separate our conversion factors so that they don't bleed into the next one, so that we keep them nice and separate. You don't have to do this. And then this horizontal line just helps us separate what's on the top and the bottom in case we're not writing in perfectly flat progressions. Again, you don't have to do it this way. This is the way that I was taught how to do it, and I like it. And then we can cancel our units along as we go with our conversion factors and hopefully end up with the units that we're looking for. When we set things up like this, this is only if we're doing a lot of multiplication and division. If we have to do addition, subtraction, we would have to do something else. When we do this, we multiply everything on the top, whatever numbers we have. And we divide by everything on the bottom. I do occasionally get questions about that, which is fine. It doesn't matter if you do all the multiplication first and then do the division. You can do it left to right, multiply, divide, multiply, divide, multiply, divide. We can switch them around. It doesn't change anything. And then the last step would just be to check. Does the size of our number seem correct? Do we have the correct units? And importantly, are the significant figures correct? And again, this physical sense part, that's something that you'll build up a sense for if it makes sense. All right, a real easy one. This is about as straightforward a question as we can get. Convert 56.0 centimeters to inches. We are given 56.2 centimeters. It's a number, we're given that. We want to convert it to inches. So we're going from centimeters to inches. Can we do this in one step? We sure can. Centimeters to inches. Our conversion factor that we're going to use for this is 1 inch equals 2.54 centimeters. We want to get inches out. That means in our conversion factor, we want inches on the top. Another way you can think of it is we want to get rid of centimeters, so we need centimeters on the bottom. So there's two forms of this conversion factor. We made them earlier. The one that we want to use is 1 inch over 2.54 centimeters. So that would be what our solution map looks like. Then to write out the actual problem, 56.0 centimeters. That's on the top, so we'll put the line under it. And then we write in our conversion factor. 1 inch over 2.54 centimeters equals. And we can see we've got centimeters on the top in our starting number. We've got centimeters on the bottom in our conversion factor. Those will cancel out. The only unit that's left is the inches. The inches come through. And then we get to pull out our calculator and solve. The calculator says 22.047 24409 inches. That seems like a reasonable enough size of a number. We've got the correct units. We just need to check our sig figs. Are we doing addition, subtraction, or multiplication, division? Multiplication, division. And when we are doing multiplication, division, we care about number of significant figures. It looks like that's 3 for both cases. Secretly, our conversion factor is exact. So we'll round for 3 significant figures. This interior 0 is our last significant figure, and the 4 lets us know that we round down. Our final answer would be 22.0 inches. Questions? Yes? Yes, we have to keep that 0 because it's our third significant figure. We've got the written decimal point, so that lets us know that that's a significant 0. All right, one for you to try. Convert 1,342 meters to kilometers. The kilo prefix is equal to 10 to the 3, which is the same as 1,000. I'll give you a little bit of time to try that. So the two things that are equivalent for this problem is that 1 kilometer is equal to 1,000 meters. So this prefix, this k, the metric prefix k, is equal to 1,000. we can swap out that K for the unit for the number 1,000, and then it's 1,000 meters. That's how we would come up with that. Or if you just know that that's true, also great. What are we given in this problem? Meters, 1,342 meters. What are we trying to find? Kilometers. So we're going to go from meters to kilometers. We can do that in one step. Since we are starting with meters, we want the 1,000 meters of this thing that's equivalent to be on the bottom. Alternatively, you can think of it as we want the 1 kilometer up top, since that's the number that we're ending with. Both of those things are true. So that's the conversion factor that we'll use to do it. So 1,342 meters, our conversion factor 1 km over 1,000 meters equals sign. And we've got meters on the top in our starting number. We also have meters on the bottom in our conversion factor. Perfect. Those cancel out. Those turn into a 1. The unit that's left is kilometers, km. So the number that we get out is 1.342 kilometers. As you get more familiar with doing these calculations with metric prefixes, sometimes you can just do these instantly because you're just shifting the decimal place over left or right a couple of places. If you're able to do that, great. That's awesome. That's going to save you some time. Just make sure you don't screw up. So for example, this question, if I put this on an exam, 1.342 kilometers would be one of the answers. It's also possible, though, that somebody might flip the conversion factor and they'd have 1,000 on top. So I might have 1,342,000 as one of the other answers. So if you got the conversion factor wrong, you might see, oh, that's the number that I got, but it's actually the wrong number. I'm just trying to prepare you so that you don't get shocked by the exam, because that happens frequently. All right, questions about this unit conversion problem? Yes?
So for the 1,000, when we're looking at significant figures, does the one on the bottom, since the zeros are ambiguous, I guess my question is, what would the n be for significant figures? Or
It is for metric prefix conversions are exact. And typically on an exam, I'm either going to be testing you on significant figures or I'll test you on something else. I won't test you on both at the same time. On homework and in labs, though, it will be looking for the correct number of significant figures. All right, so that was all single-step problems. We can also do some multi-step unit conversions. It's the same process. We just have, as the name implies, multiple steps. So we want to convert 194 centimeters to feet. We're going to need to employ more than one conversion factor to get there. One of the ways that we know that that's true, it says multi-step unit conversion problems on the header of the slide. What can we convert to from centimeters? Inches. Can we convert from inches to feet?
Yes.
Perfect. So this is a two-step problem. We're going to need conversion factors to do those steps. So you might go look up in a table, you might ask Google, you might pull out your yellow sheet that I forgot that I had printed and I need to go get. And find the conversion factor between centimeters and inches. It's 2.54 cm equals 1 inch. Since we're starting with centimeters going to inches, we want the inches on top, the centimeters on bottom. So this is the correct form of the conversion factor, or the easy form of the conversion factor. If you go through the work of setting up the conversion factor and then you get to putting the problem together and you're like, that's not the right one, flip it. You just flip-flop the top and bottom. Sometimes that's all it takes to go from having a wrong answer to having a right answer. And then for inches to feet, 12 inches in 1 foot. Same idea, we're going to feet. Feet need to be on the top. And 12 inches on the bottom. And then putting it all together, our starting number, 194 centimeters. Lay out that line to separate our top and our bottom. Plug in our first conversion factor. Vertical line to separate from our second conversion factor. And then we can check and make sure our units cancel out. So we started with centimeters. We have centimeters on the bottom in our first conversion factor. So those will cancel out. And that first step, we got to inches. That's where we wanted to be based on our solution map. So we're following along perfectly so far. So 12 inches on the top. We've also got 12 inches on the bottom. Those will cancel out. The unit that's left is feet. And so we'll pull feet through to the end. Plug that into the calculator. 6.364 and some other stuff, feet. We had 3 significant figures in our starting number. Both of our conversion factors are exact, so we'll get 3 significant figures out. 6.36 feet.
How did you get that? Do you divide from 1 and 4 by the 2?
Yeah, so here's what I put into my calculator. 194 divided by 2.54 divided by 12. You can also write out, if you don't mind putting parentheses, 194 divided by, open parentheses, 2.54 times 12. Those are both correct solutions. If you put in 194, this right one, divided by 2.54 times 12 without the parentheses, your calculator does 194 divided by 2.54. It gets an answer, and then it multiplies it by 12 rather than dividing it by 12. So you either need the parentheses or you need the divide sign twice. I do the divide sign twice because it saves me pushing a button twice. Either of those will get you the correct answer. Other questions? All right, another example question. The instructions on a box of pasta says to boil 2 gallons of water for cooking the pasta. How many milliliters is that? So we've got 2 gallons that were given. And we're asked for milliliters. This one's laid out pretty simply, right? What we're asked for is in its own complete question sentence. We're trying to convert that to milliliters. So going from gallons to milliliters, mLs. There's a couple of ways we can do this, a lot of ways, since we're just doing a unit conversion question. So you could convert from gallons to quarts, from quarts to pints, from pints to cups, from cups over to milliliters, or you can convert from gallons to liters to milliliters, or you can convert from gallons to quarts to liters to milliliters. There's a lot of different ways that you can skin this cat. There's not really an infinite, but basically an infinite number of different ways that you can solve this problem. As long as you can show that the units cancel out correctly and you get the same answer, then it's a good solution, in my mind at least. So I want to do gallons to liters. And I know that I can get from liters to milliliters because all that we're doing there is a metric prefix. I forgot my yellow sheet with all the conversion factors, and I don't have the gallons to liters ones memorized, so I just asked Google, hey, what's gallons to liters? And 1 gallon, as it turns out, 3.785 liters. I want to get rid of the gallons that I was starting with to go to liters. That means I need the liters part on the top, the gallons part on the bottom. So 3.785 liters over 1 gallon will be my conversion factor. For liters to milliliters, milliliters is 1,000 off from, there's a factor of 1,000. If you don't remember which one goes with which, that's fine for now. Which one's bigger, a liter or a milliliter? A liter. So if they're different by 1,000, a liter is bigger, so the 1,000 gets to go with the milliliters. That's often how I do it, or at least did it, when I was solving these metric problems, since a lot of them are increments of 1,000 between adjacent prefixes. We need to go to the milliliters, so milliliters on top, and our 1 liter on the bottom. We've got our 2 conversion factors. It's a 2-step problem. So now let's write out the whole calculation. 2 gallons, first conversion factor, 3.785 liters over 1 gallon. This is going to get our gallons to cancel out. Our second conversion factor, 1,000 milliliters over 1 liter. This will get our liters to cancel out. Usually when I'm doing problems and I'm canceling units out, this is just for your reference for looking back on notes, I will match the direction of the way that I cancel them out so you can see which one's canceling which. You don't have to do that. I'm just letting you know that's how I do it in case that it's helpful for somebody. The units that are left are milliliters. Perfect, that's what we wanted. And when we go to put this into our calculator, everything on the top gets multiplied. We divide by everything on the bottom. In this case, it's just 1s on the bottom. That's not going to change our answer. I'm not even going to bother putting in 1s if I have them in my problem. So 2 gallons, just the 2, times 3.785, times 1,000, and that should get us some big number of milliliters. It's 7,570 milliliters. Milliliters are pretty small, gallons are pretty big. Seems reasonable to me. Is this our final answer? we get to do something with significant figures. This 2 gallons at the beginning, it's just one number. That's one significant figure. Might have been better. Probably doesn't matter because we're just cooking pasta, but if we had more significant figures, that would be cool. One significant figure, we've got 4 in our first conversion factor. Our 1,000 over 1, it's a metric prefix, that's exact, so we don't need to consider it. We're going to be taking one significant figure through for our final answer. So this is going to round up to 8,000 milliliters. And then we get to write it in scientific notation. So 8 times 10 to the 3 milliliters, final answer. Some questions on the exam might have only answers in scientific notation. So you will have to be comfortable converting to and from scientific notation. All right, I use 25 grams of coffee beans to make a cup of coffee in the morning. If I buy a 2.00 pound bag of coffee from the grocery store or online, how many cups of coffee can I make before I need to buy more beans? And go. One of the conversion factors you'll need is 1 pound is 454 grams. There's another secret conversion factor that you will need. So I mentioned there's a secret conversion factor in this problem. Before we get to that, let's identify the things that we're given. We're given some information here. Oftentimes, the stuff that we're given is going to have a number in front of it or a number involved in it. 25 grams of coffee beans, that's a number. 2-pound bag of coffee, also a number. And what are we looking for? Cups of coffee. Right next to our question word, our question phrase, how many? So cups of coffee is what we're looking for. We can write that at the end of our solution map. And what do we think we're going to start with? 2 pounds or 25 grams? In this case, it is pounds. So 2 pounds of coffee. I gave you one conversion factor that had pounds in it. A little hint that we're converting to grams. So we'll convert from pounds to grams. Do we have something that relates grams and cups of coffee? The first sentence, right? 25 grams of coffee beans to make 1 cup of coffee. So this is actually a conversion factor. It's sort of hidden because it's a word problem. I know lots of people hate word problems. So this is the key to cracking the how often do I have to buy more coffee. That is actually a conversion factor. So the 2 pounds to grams, we're putting the 454 grams on top. We're trying to go to grams, so grams needs to go on top. We're trying to get rid of pounds at the same time. You know, lose a little weight, doesn't hurt. So putting pounds on the bottom is a joke. And then for our second step, relationship between grams of coffee and cups of coffee. That equivalency is that 25 grams goes on to create 1 cup of coffee. Since we're trying to get to cups of coffee, that'll go on top. The 25 grams will go on the bottom. One cup of coffee over 25 grams. Any questions about the solution map setup so far? So occasionally we will have those conversion factors. You have to find them in the problem. You have to be able to identify them. It helped that we were able to set up the first step, and then we could see that grams and cups of coffee both showed up in that first sentence. Occasionally this will happen in the questions that we have to solve for the class. All right, so 2.00 pounds. We could have that unit of coffee on there as well if we wanted to. It's kind of optional. Our first conversion factor, 454 grams over 1 pound. That's going to cancel out the pounds. Our second conversion factor, 1 cup of coffee over 25 grams. This is where we would also need to include coffee if we included coffee at the start. So the grams cancels with the grams. Right, these two with the backslashes through them. And the coffees would also cancel in this case. Optional, if you include those for this question. So all that's left is cups of coffee. What we're putting into our calculator, 2 times 454 divided by 25. The 0.00, completely optional. Your calculator does not care if you include that. The answer, 36.32 cups of coffee. Going to round that to 2 significant figures because of this 25 grams number. So 36 cups of coffee. Question? So we use the 25 because it's just 2 significant figures. It's just the 25. If I said that I use 25.0 grams, which is generally true, then we would have 3 significant figures, and then they're all 3 significant figures, so it would be 3 for the final answer. Other questions?
And then you multiply the top and then divide by the 25 on the bottom, right?
Correct. Yes, multiply the top, divide by the bottom. Other question?
Does cups of coffee not count as something counted in whole numbers? Or if we have a word problem with something counted in whole numbers, will we know that we don't have to account for the significant figures?
So this is another instance of I'll test you on one thing at a time. So in this case, yeah, we would logically, like for at home, 0.32 cups of coffee doesn't do me any good. I'm not going to waste my time brewing a third of a cup of coffee. It's going to throw everything off with my process. So I would also round this to 36 cups of coffee and then just carry over the 0.32 to my next bag. But yeah, it would have the problem if this shows up, something like this on the exam. All right, last thing that we'll talk about very briefly here. We can also have unit conversions where we convert multiple units. Units in the numerator, the top of the equation, units in the denominator, the bottom of the equation. An example of this, a hybrid sedan, a Prius, for example, has an estimated city fuel economy of 48.0 miles per gallon. In Europe, they use kilometers and liters petrol. We've got some conversion factors. We want to calculate the fuel economy that the company would advertise in France, for example. So our starting bit is miles per gallon. How should we write out miles per gallon?
Miles over gallon.
Miles over gallons. Oftentimes you'll see this as mpg. The P per means divided by. So 48.0 miles divided by gallons. And you can either write them out to the side like this with the units, miles over gallons, or you can lump 48.0 miles together and put gallons underneath the whole thing. I'll show you what that looks like. You can also write it out like this. Combine your numerator, and then you've got single gallons on the bottom. So we're trying to convert miles per gallon to kilometers per liter. We need to swap out our miles for kilometers. Those are both units of length. We're keeping units of length in the numerator. Gallons, a measure of volume. Liters, a measure of volume. Those are in our denominator. So we need to set up conversions so that those units change. Let's convert miles to kilometers first. So we'll have kilometers per gallon as an intermediate number or units. And then we can convert the gallons to liters after that. For this first step, converting miles to kilometers, which of the two units needs to be on top in our conversion factor? Is it miles or kilometers that should be on top? Kilometers, because we want to get kilometers on the top. Another way we can think of it is we want miles on the bottom to get rid of miles. So 1.609 km over 1 mile. That'll be our first step conversion problem. And then our second step, we're converting kilometers per gallon to kilometers per liter. We need to swap out this gallons in the bottom for liters. So when we're putting together our conversion factor, which one do we want on the bottom, gallons or liters?
Liters.
We want liters to be on the bottom because that's where liters should end up. We also need gallons to be on top so that it will cancel out with the liters that we have, or the gallons that we have, sorry. I'm going to scooch all of this. Scooch. Okay. So our two conversion factors, 1.609 km over 1 mile. We've got miles on the top in our given, we've got miles on the bottom. In our conversion factor, those will cancel out. Yay! Let's say we didn't set up a solution map and we just threw in the conversion factor and we threw it in upside down. Let's see what that looks like. That would be putting 3.785 liters on top and 1 gallon on the bottom. We've got kilometers on the top, we've got liters on the top, we've got gallons on the bottom twice. That's not right, so that would be one way that we could catch this mistake. If we just went ahead and did this problem as written, our units would be kilometers, liters per gallon squared, and that is what I call nonsense units. It doesn't mean anything to anyone, especially not me, especially not you. That's a good sign that we did not do things correctly. So we would flip our top and our bottom. And discover, okay, we had our thing upside down. Obviously, we did it correctly when we were setting it up in class. Now we've got a gallons all the way over here on the left in the denominator. We've got a gallons in the numerator of our conversion factor. Those cancel out. The units that come through are kilometers per liter. And we can toss all those numbers into our calculator. It would come out as something like 20.4 kilometers per liter. Questions? All right, we will pick up just after this next week.